Hello friends, welcome to this video. In this video, we will implement the UNET architecture in the TensorFlow framework and apply it to the brain tumor segmentation dataset. So first of all, let's have a short introduction about what is UNET. So here is a short article on what is UNET. Let's go through the article. So UNET is an architecture developed by Olaf Roneberger et al. For biomedical image segmentation in 2015 at the University of Freiburg, Germany. It is one of the most popularly used approach in any semantic segmentation task. It is a fully convolutional neural network. So when you say fully convolutional neural network, is that we use only convolution layer here. We don't use any dense layer or fully connected layer. So this is the diagram, the original diagram of the UNET architecture. So fully convolution has a benefit that you give any image size, it would output the same size mask. So it is independent of the size, but still when you train a UNET architecture with a fixed size, just test it on fixed size. If you change the size, the performance affects. Okay. So you can read this article. I'll give you the link. Now we'll directly move on to the implementation part. We'll work on the implementation. So here I have imported all the layers. First we require is a convolutional layer. Then we have a batch normalization, then activation, max pool 2D, con 2D transpose, concatenate, and finally the input layer. After that we have imported the model class, which would take the input and the output of our UNET architecture and build a model out of it. So first of all, we are going to implement the con block. So let us define a function called con block. The con block would take an input. It would be input feature map. Then it would take number of filters, or you can also call number of feature channels. So these are the output number of feature channels. Okay. So this con block basically contain a convolution layer, batch normalization layer, activation layer, and again these three layers would be repeated. So in short, we have 6 layers. So we begin with con 2D layer. First would be number of filters. Then kernel size. So we use a kernel size of 3 by 3. Then a padding. For padding, we're going to say same. So now we're going to give input to this layer. So input would be the input of this con block, or the argument of this function. Next, it is followed by the batch normalization. So one thing I want to say here is that in the original UNET architecture, no batch normalization was used because it wasn't invented at that time. But now in the 22, we use it because normalization layer is basically a norm now. You will use it in between convolution and an activation function because it stabilizes your training. It helps to improve your performance. So we are also going to include it. Batch normalization, and the input to this batch normalization layer would be output of this con, so X. Next it is followed by the ReLU activation. So ReLU is an activation function, basically a non-linear activation function. So it adds non-linearity to the network. Now we have 3 layers here, so we're going to copy them because we need to repeat same set of layers. We're just going to change the input from inputs to the output of this activation function. So our con block is done. So we need these 6 layers in the both the encoder part and the decoder part of the network. So we have built a function, so we just simply need to call this function and we're done. Next we are going to implement the encoder block. So encoder block have inputs as one argument and number of filters as second argument. So in TensorFlow, when I say number of filters, so it basically means number of output feature channels. Okay. So first, the encoder block would have this conv block. So it would take inputs and the number of filters. So we're going to copy them from here and paste them here. After that, it is followed by a 2 by 2 max pooling. This is 2 by 2. Input would be x, and we're gonna return two values, that is x output of convolution layer or the output of cone block, and p the output of pooling layer. Here x would act as a skip connection and p would act as the output of the next layer. So let us go back to the diagram. So if you see this gray arrow, this is basically output of convolution layer and it acts as skip connection, and this downward arrow is basically max pool 2D. It goes to the next encoder block. Okay, now let us implement our architecture, that is UNET. So we're going to say build UNET. So it's going to take the input shape. This is its argument. First of all, we're going to implement an input layer. We're going to call it inputs. It's going to take this argument input shape. So we have our input layer. Then we have 4 encoder block. So we have implemented the encoder block just now. So we're going to call it here, and it return two output. First is this skip connection, second is this pulling. So in short, we're going to say s1 comma p1 equals to encoder block. We are done. Then first input would be input layer, then number of filters, and in UNET number of filter began with 64, and in each decoder block the number of filters doubles. So let me, if I copy the encoder block, okay, then this would be s2 and p2 encoder block. Now the input to the second encoder block would be output of the first encoder block, that is p1. Then number of filters would double, that is 64 into 2, 128. Now let me just copy this again. This time it would be s third and p third. Input would be p2 and number of filter 256. Now we're going to copy it last time. We're going to call it s4 p4 encoder block. Input would be p third and number of filter 512. So now we are done with our encoder. Okay, so let's run this part of the code and see if there's any issue here, because error would always come. Error would not leave you. First input shape. So our input shape would be 256 by 256 by third. We're going to call our method or function, give it this. So now we do not give anything from this function. So what we do, we're going to print the shape of, let's say, first the skip connection, s1 dot shape, s2 dot shape, s3 dot shape, and s4 dot shape. Okay, then we're going to print the shape of all the p1, p2, p3. Okay, so now we're going to see the shape of s1, s2, s3, s4, p1, p2, p3, p4. Okay, so let's run this. Okay, so you can see a lot of messages from the TensorFlow. Now if you go to the last, you can see first shape, second, third, fourth, then first, second, third, fourth. So now the top one belong to skip connection. So first skip connection shape is 256 by 256. So it is exactly same as the input layer. Then second is 128 by 128 because it passed through pooling layer where it decreases by factor of 2. And again 128 by 128 became 64 by 64, and at last it became 32 by 32. Same in the pooling, you can see it began with 128 then 64, then 32, and at last we have a feature map of size 16 by 16 with 512 as number of filters. Now let us again go back to our code. Now let me comment these out. Now here we have a bridge in between encoder and the decoder, and bridge would be our cone block. So we're going to say B1 cone block, P4 as the input, and 1024 as the number of filters. So now the encoder and the bridge is completed, or you can say the bottleneck layer. Okay, now comes the decoder part. Let's implement the decoder block. It's also simple, not that difficult, just a bit of understanding is required. Decoder block. So first of all, decoder would take the previous input feature map, and here it would begin with B1. So let me just give it inputs. Okay, then it need a skip connection. So if we remember from here, so we are here. Okay, so this goes to there, this bridge. Here you can see the up cone. After up cone there is a concatenation, so we need this skip connection. So we're going to call them skip features, and after that we require number of filters. Okay, so for now I'll remove these just for explanation, because here I need a layer. So first of all, what we do, we'll take the previous feature map and upsample it using transpose convolution. For that we're gonna use cone 2D transpose. We're gonna say number of filters, convolution size would be 2 by 2. So UNET uses a 2 by 2 up cone. Up cone basically means cone 2D transpose layer. Strides would be 2, because we want to upsample it by a factor of 2. So we want to convert 16 by 16 to 32 by 32. That is why we are using a stride of 2. And padding would be same. Input would be inputs. So what I'll do now, I'll call this decoder block here. Okay, it requires input B1. For now it requires two inputs, that is previous input feature map and number of filter. So in decoder the number of filters decreases by a factor of 2. So from 1024 it became 512. Now I'll print the shape of B1. Let's do it inside the decoder only. Inputs dot shape. Now just see the shape of X. It would be increased by factor of 2. So you can see we have two shapes here. First is this inputs, second is X. So input has a shape of 16 by 16, and when it goes to transpose convolution, it upsamples by factor of 2 and became 32 by 32. So let's say you put a stride of 4 here. See what happened. Let's see if it works or not. So now I can see it is working. From 16 by 16 it became 64 by 64. But we're going to put a stride of 2 because that is what is mentioned in UNET architecture. Now next comes the skip connection concatenation. Now if you see the shape is, let's save and run it again. The shape is 32 by 32. So we need a feature map from the encoder whose height and width are 32 by 32. So the height and width should match between the output of transpose convolution and the skip connection. So now what I'll do, I'll uncomment this part so that we can get the shape. Now we don't require this. We just need to check this shape and this shape which matches to each other. So you can see skip connection shape. So we need a skip connection with the size 32 by 32. So this is S1 and S2, S3. So you can see S4 matches. It has exact same height and width as the output of convolution layer. So what we're going to do, we're going to say skip features. We have add this argument. Now here we will add S4. What we're gonna do, we're gonna simply say x is equals to concatenate. So we're gonna concatenate both x, output of transpose convolution, and skip feature, that is feature from encoder. So we're done. Now let's print the shape of x. Let us comment out this part, run it again, see for any error. Okay, so you can see now it became 32 by 32 by 1024. So number of feature channel now doubles. After that it is followed by the cone block. Input would be x, the concatenated feature map, and second would be number of filters. Now it is done. We're going to return x. So this is the simple decoder block. So it returns G1, let's say. We need G2, that is second decoder block output. Decoder block input would be D1, the output of first decoder block. Skip connection would be as third now. Can calculate the same as printing appropriately. Now number of filters 256. Then third decoder block. Just see, number of encoder block and number of decoder block would be same, that is 4. Because we sequentially decrease the height and width of the feature map, and then we sequentially increase the height and width of the feature map. And skip connection S1 64. So this is the decoder block. So now the output of D4 should have a height and width same as this, the input 256 by 250. So let me just print this. So if you see 256 by 256, just number of feature channels are 64. Because now we are working with binary segmentation. In binary segmentation the number of class is 1. So now we'll have a simple 1 by 1 convolution layer where number of feature channel would be 1, kernel size would be 1, padding equals to same, and activation is sigmoid. And input would be G4. Now let's print the shape of this outputs. Let's see the shape. Now I can see 256 by 256 by 1, and this is the shape of the required mask. Now we have both the input and the output. Now we're going to build our model. So we're going to say model equals to model. First we're going to give the input shape, not the shape, the input layer and the output layer. Let's give it a name and call it UNET and return this model. Let's complete this function. It's going to give some model, and we're going to say model dot summary. Now let's run this and check. That's the summary of the model. So you can see there's this much amount of parameter, and where this much is trainable and rest 11,000 are non-trainable. You can see the entire structure. If we go from top, you can see the input layer 256 by 256 by 3rd, because we'll input an RGB image. The number of parameter here are 0. Then we have cone 2D layer, then base normalization, activation, then again convolution, base normalization, then activation, and after that we have a max pooling where height and width are reduced by factor of 2. So like this, all the shapes, names and everything is given in this summary. So this is about the implementation of the UNET architecture. I hope you'll have a good understanding of UNET architecture now. If you still have any query, any question, just write it down. Okay, write that below and I'll try to solve it in any other video, or try to put it in next video. So if you come to this part of the video, this means you are enjoying the content. So please make sure you hit the like button and subscribe the channel. Now we'll move on to the training part of the video. Now we are in our train.py file. Here, first of all, we are going to import all the libraries which we require. So we have a lot of libraries here. First is OS library, and second, if you see, we have a statement, this os.environ, then tf underscore cpp min log level 2. So if you see, have seen, we got a lot of message when we run any TensorFlow program. So this is just to get rid of those messages. Okay. Next, we have imported the numpy, because we're going to play with images, and images are going to read as array, and numpy is a useful tool to manipulate array, work with them, and a lot of stuff we can do. After that, we have cv2. So cv2 refers to OpenCV. So this is the library we're going to use to read, resize, and write back images. Next, we have globe. The globe we're going to use to extract the images path and the mask path very easily. Then we have the shuffle. So we're going to use to shuffle the list of images and the mask. After that, we have imported a lot of stuff from TensorFlow. So first is we have imported the directly TensorFlow STF. Then we have imported some callbacks. I'll explain them to you. After that, we have imported the Adam optimizer. Next, we have imported the train test split function from the sklearn library. So we're going to use this function to split our complete dataset into 3 different parts, that is training, validation, and testing. Next, we have imported the UNET which we have built now. Okay. After that, we have imported 2 matrices from matrix.py, and these are dice coefficient and dice law. In this video, we're going to use dice laws because it is much better than cross entropy. So let's now continue with the coding part. Before that, let me just show you the data set. So these are the 2 folders. First is images, then mask. Each of the folder contain near about 3064 items. So that is the size of our data set. So you cannot say this is small, this is really good data set. Now let me just show you some of the samples. So you can see this is the image of a brain. So we have different view, different perspective. So this would help us to make the model more robust, because it can now deal with different perspective and slices, every other thing. Now these are the images sample. Now if you see the size, these are 512 by 512. But this dataset also has some sample which are of size 256 by 256. So that is why we'll work on a size 256 by 256. So we're going to resize all the images to this size. Now the mask. So it's a binary segmentation problem. It only has one main class, that is this white patch, that is the tumor, and the rest black area is the background. So these are the masks. It has different kind, different quality of. This is about the data set. Now let's move back to the coding. So first of all, let's define some global parameter. And these are height and width. So height 256, width 256. So we have initialized them at the top only, so that any function, any library can use them easily. Next, we're gonna write a function called create dir. So we're gonna give it a path. So this function is going to help us to make some folders which we require for our task. So first of all, we're going to give it a path. Then we're going to check if that path exists or not. If not, if that path do not exist. If that path do not exist, then create that path or folder. As simple. So now let's start with our main statement. This main statement basically tells us that the execution of program begins from here. So first of all, we are going to seed the environment. Seeding is really important for reproducibility. because neural network are initialized randomly, so you do not want to change your randomness again and again. Maybe on my system randomness is different, so I'll get some different performance, you get different. So it is important to seed your environment, so we all have same randomness. So that is why we'll try to seed. There is some function in CUDA library which affect your reproducibility, but still seeding is important. Next we're going to use our create dir function to create a directory for storing files. So we can say for storing file. Yeah, this is fine. So we're going to call this function, we're going to say file. Next let's set some hyperparameter. Okay, before that let me just show you if that works. So if you see, these are the 4 files we have. Now what I'll do, I'll execute the code. You can see it work without any error. So now if you see, we do not have those lines which shows us here. This is the effect of writing that line on the top. This line helps to get rid of all those unnecessary messages. Now I executed the code. Now if you see, we have a files folder here. So this create dir function help us to create empty folders or directories. Next we're going to set some hyperparameter. So first of all, let's set the batch size, that is 16. Learning rate is 1e minus 4, and number of epoch, let's say 500. Then we're gonna have 2 path. First is model path, then a CSV path. So we're gonna say model. So model path is basically the place where we'll store our weight file. So we're gonna save our data inside this files folder, and the name of the weight file would be model.h5. Then CSV path, again os.path.join, folder name is files, name of the file would be data.csv, or you can even say log.csv. Log.csv is much better. Now if you see, I have set a batch size of 16. Okay, this is up to you and it depends upon your system, because I have RTX 3090. I know this is much expensive, but not now, and it has a GPU memory of 24 GB. So with that memory I can set a batch size of 16 and it would work perfectly fine. Okay, so don't use 16, maybe it won't fit on your GPU, don't work on you, so try to change it. Okay, make it 8 4 2 1, just try to see if it work, which batch size works for you. Okay, so don't just copy it like that only. Okay, and hyperparameters are basically things to play with, so you can play with these 2 things, like batch size you can play with, learning rate you can play with. Okay, now let's write a function to load the data set and split them. Def load dataset. So this is the name of the function. It's going to take the dataset path and split size. So let's say by default a value of 0.2. 0.2 means that 20% of the data would be used for validation, and another 20% would be used for testing, and remaining 60% would be used for training. So this means we are doing a split of 60 20 20, that is 60% for training, 20% for validation, and rest 20% for testing. Now let's load images first. So we're going to say images, so it would be a list. First of all, let's set a path. First would be path, then if I show you, the name of the folder is images. Okay, and for mask, right, images, and after images we can write star. So star basically means load all the files which are inside this folder. So the extension of our images is .png. So we're gonna say star.png. So this basically means load all the file which begins with which can begin with anything. They should definitely end with .png, and that is the case with all our images. I've done this just because in case there's some text file or any other file, because with dataset comes the explanation file. Just by to avoid those things, we just want to specifically mention that we want to load all PNG images. So this is a path. Now we're going to use our globe library. Okay. So this globe would give you a list, and we're going to sort that list. Just make sure you sort that list. I'll show you what happens if you don't sort. So let us now load all the masks. Instead of images, we're going to say mask. So now let's load the data set. So we're going to say dataset here. Let's call this function. We can say dataset path. Let's go the default value. For now, I'll paste my dataset path. Paste it here only, not there. So this is a path to the dataset. Now I'll execute it. Okay. Now I'll just remove this. Maybe the program work without sort, and maybe not. But why take risk? Okay. So what I'll do is I'll print, because it's gonna be a list. So I'm gonna print that string, that is the file path, image or mask path at the index position 0. So now if you see, it's working fine without sorting. Also it has 1.png, and here also it has 1.png. Okay. So in some case when the naming is a bit different, okay, or randomly it has 1.png and it has 2.png or 10.png. So to make sure these things don't occur, we sort the list, because when naming is same or nearly same, sorting would sort the name in a specific order, and that order makes sure that you get appropriate image and mask. Because in most of the data set, the naming of images and mask are same, just to correspond that this image belong to that mask and that mask belong to that image. So just make sure you sort them. It won't take that much time, just to be sure that this would work. Now we have loaded both the image and mask. Now what we'll do, we'll split them. So first of all, we need a test size, so we're going to call it split size integer length of images into split. So this is split size, like how many samples you want in your validation and test set. That is split size. So now you can easily manipulate this and it would be automatically done. So we're going to first split the dataset into training and validation. So here X refers to images and Y refers to mask. Just I use this thing in variable naming. We're going to use train test split. First images, simple, and test size. Test side would be split size, and now a random state. So this random state is basically seeding, because some random operation are going to happen here and it's going to split the image list into two different lists, that is train X and valid X. That's why a random state. Just make sure you same random state always. Don't specify anything, it would randomly split it. We run program again and again. I'll copy this again. Now I'll instead of X I'll say Y. Train X and valid, no, train Y, valid Y, and instead of images I'm going to say. So this way we have splitted the data into training and validation. So now train contain 80% of the data and 20% is assigned to validation. Okay. Now we need to make test set. So we're going to say train X and test X. I know there are much better way to do this, but I'll stick to this only. I'm going to copy this from here And now we'll take this train X, which contain 80% of data. So what we'll do, it take this train X data and assign 20% to this. So the train X would become 60%. Now we'll change X to Y, and inside it train Y. This would work perfectly fine for us. Now we're gonna give back those training, validation, and testing. Now let us call them here. So we have called. Now what we'll do, we'll print the length of those data sets. Let's put a gap here. Now we're gonna run this program again, just to see if everything is working fine. You can see 1840 images are used for training, and 612 images are used for validation and testing set. I think this split is okay for me. It's 60 20 20. You can do it like 80 10 10 or up to you, or 50 25 25, because the data set is large. It's up to you. Okay, so data set processing is done. Now we'll make a pipeline for training the. First of all, we'll define some function here. First is reading image. So it would take a path. So first of all, we write a statement to decode the path, because this function is going to be used by the TensorFlow, and it would give you string s encoded. So first of all, we're gonna decode that, and then we're gonna read the image. We're gonna read this as RGB image. I know the images are grayscale, but still I'll read them as RGB. You can read them as grayscale, and the input here would change from 3 to 1 when you call this function here in this train.ppy file. So let's read it as RGB. Path. Then we're going to resize it. So X as the array, then width by height. Then we're going to normalize the image pixels by dividing them with 255. So now till here, the pixel range is between 0 and 255. So this is really huge. So what we do, we divide the all pixel values with the maximum pixel value, that is 255. So this way it would convert in the range of 0 and 1. So it would be like 0 0.1, 0 0.2, 0 0.25, 0 0.68, 0 0.92, something like that. Would be. So now we'll convert it to float 32. Okay. Now we're going to give this value back. So this is done. Now we're going to move on to the read mask function. Again, we're going to decode the path, copy paste, and this time we're going to read this image as grayscale, because it is literally the mask just black and white. Because the output, if you remember, the output of our function is 256 by 256 by 1, so it is one channel. That is why we're reading it as a grayscale, because grayscale is by default one channel of. Okay, so now we're going to give path here, then we're going to read it as grayscale. Okay, so again we're going to resize it. So we're going to simply copy all these steps from it, because they're literally the same. Just one step need to be added here. So we resize it, done. We normalize it. So in mask, normalizing would also be same. Now you may question. Let me just give you a mask. Okay, so this is one of our masks. So black region is basically pixel value is 0, and white is pixel value 255. So we divide that 255 with 255, it became 1, and 0 divided by 255 remains 0. So it normalizes in the range of 0 1 0 1 or 0 and 1. Now just a really simple thing, what we need to do, we need to expand the dimension here. Next, expand dims x axis. Okay, so what happen is when you read the grayscale image, it would be of, let's say, height by width, just that. You resize it, it again became some specific height and width. Here also the dimension remain change, here also, but here what happened is we added the dimension like this. I hope you get it, why we have added this expand dimension line here. Okay, so reading image and read mask function are done. Now let's build another function called tf. Tf parse would basically take a single image path and a single mask. Okay, now inside it we're going to build another function called parse. This also take individual image and mask. Okay, here we're going to call both our read image and read mask function. Read image x y is equals to read mask. Okay, and we're going to return both the x and y. Now this simple function is done. Now what this simple function is done, it take those paths and give us our arrays which we require. Now if you see, we are using the OpenCV and the NumPy function which are outside the TensorFlow, so you cannot directly include those libraries or functionalities into the TensorFlow. So for that reason we're going to call tf.numpy function here, and we need to call this function. So we're going to type this function name, then the input, that is x and y, and after that we need to specify the output data type. So output data type is float32. So we're going to say tf.float32. Now it would return x comma y, that is the image and mask tensor, I believe. Then we need to set this shape. First is height, then width, then here we are reading it as RGB image, so number of channel would be 3. Then y dot set shape, here height would be same, width would be same, number of channel would be 1, and we're going to return x and y. This is simple function which takes both these functions. So you can also directly use TensorFlow functionality to read, resize and do everything, but I feel this OpenCV is like best because I'm using this, so I'm got addicted to this way only. Maybe in some next video I'll try to give another way where you can directly use TensorFlow, so you need not to go through this step, I think. Okay, now we'll have another function tf.dataset. I know we have going through a lot of function, but just bear with me some more time. So here this is our last function in our dataset pipeline, not entire file, just the dataset pipeline. Here x is a list of image path, y is a list of mask path. So we're going to say dataset equals to tf.data.dataset.from tensor slices. Then we're going to give x and y. Oh, my mistake. Okay, so now what we do, we're going to again say dataset to dataset. We're going to call the map function of it, and we're going to use this tf parse. This basically takes this list of and use this tf parse function to read all the individual images and mask. Then what we do, copy this and form a batch. We give a batch. Okay, so by default batch is set to, okay, let's default is 2 years only. Okay, then prefetch. So prefetch is basically a function where while the model is training on epoch, not epoch, it's training a batch, it would load some batches in advance. Now we're going to return dataset. Okay, so the dataset pipeline is this only, it's enough. Now what we do is simply say train dataset, and we're going to call tf dataset. We're going to give it train x and train y. Remember, it take list of images path, list of mask path, and then batch. Batch is equals to the batch size, that is 16. And same we're gonna do to valid dataset. TF dataset. We're gonna call valid x and valid y here. We're gonna set the same batch size. For validation, I think you can increase the batch size, but let's not get into that. Let's remain simple. So this is till now we work on the dataset pipeline. Now I'll just run this one for you for x comma y in train dataset. So x and y are basically batches of images and masks. So what I'll do, I'll print their shape. Okay, I'll run this for you. If you see a batch size of 16 and 256 by 256 by 3rd, and same for the mask. It will run, and after some time it would end. So let's stop it because it would take some time. Now we're going to call our model which we have implemented. So let's write some comment. Model. Now let's call our UNET architecture. We're going to say model is equals to build unit. It's going to take an input shape, that is height. We already specified width, number of channel 3. If you remember, we have reading the images as RGB. Now we're going to compile the model. First we're going to set the loss as dice loss. I already told you. Then optimizer. Atom would be our optimizer with a given learning rate, that is 1e minus 4. Then a matrix just to test the performance during training. That is coefficient. Now we're going to write all the callbacks. So I'm just directly copy paste them. So here we have 4 callbacks which we use. First is model checkpoint. So model checkpoint basically save the weight file during training. So it only saves the best weight only. That is, let's say your loss rate is increasing. So when your loss rate increase, that's not the good performance. So your weight file would not save. But when your loss is decreasing, especially the validation loss, when it decreases, it saves those weight file epoch after epoch. Okay. Let's say in between some it does not decrease, it would not save. So with this check, this callback, that is model checkpoint, we would save our best weight file. Okay. Second is reduce LR on plateau. So this basically checks your validation loss, and let's say for 5 continuous epoch your validation loss is not decreasing, so decrease the learning rate by a factor of 0.1. Next is CSV logger. So this callback basically generates a CSV file and save all the training data in a CSV file, so that we can check that file after the training is complete, and we can build graphs or charts using that. And last callback is early stopping. So it also monitors your validation loss. Let's say for a continuous of 20 epoch, your performance, the performance of your loss does not decrease. Okay, then it would stop the training. So this basically stops your training to make sure that you do not unnecessarily train your network when it's not giving you performance. So you can increase it, it's up to you. You can play with this value, you can set it to 50 or 100, it's up to you. But as I'm using a home computer, I do not want to run it unnecessarily. Maybe you are using Google Lab, which is free, so you can maybe you make it 50, because our best checkpoint would be saved. So it does not affect the performance of the save weight file. So that this is about the callback. Now we'll finally call our function model.fit, and that is the last function for training. At the end we generally just call this. So you take a training data set, number of epoch, validation data set, and call. So I'll just save it and run it for once just to show you. I have already trained this model for some epochs, and I'll directly copy paste that weight file. So if you see, it does not take that much time, just 18-17 seconds, but I need to run it for long time. So let's run this epoch and see the save weight file and every other thing. Okay, so our first epoch is done. Let me just stop it here. So if you see, it's the loss, the validation loss. If you see, it decreases for infinite. So initially it is infinite, then it became 97. But this is validation dice. So all these matrices values are saved in your CSV file. So let me just stop it, clean it, and just show you those weight file. Okay, so for now, for this scenario, this is your CSV file, because we have trained it for only one epoch. So you have training dice, loss, learning rate, validation dice, then validation loss. So this is how all your values are saved, and you can build different charts, graphs using this. Okay, and this is your weight file. What I'll do, I'll delete those and I'll show you mine one. I have already trained the model and I'm going to copy those files. Okay, now just see the data.c. So this model is trained for about 61 epoch, we can say, because it begins with 0. So we have trained it for 61 epoch, and it has automatically stopped. So if you see, validation loss is decreased to 0.18 and validation dice coefficient is increased up to 81%. And if you see the training dice, it is 95 and training loss is 0.4. I believe the training is enough for this. Now the training is done. I will move on to the testing part. Here we are in our test.py file. So first of all, again, we're going to import all the libraries. Okay, so let me just go through the library which are new. So first is this TQDM. So TQDM is basically a progress bar, because here we're going to loop over the list of test images. So we just use this TQDM function, and it would give a progress bar that would tell that like out of 612 number of samples or loops, this much loop is done, this number of iteration. So basically simply a progress bar, just to show you how much stuff is done, how much is left. Next is this custom object scope. So this is used when you have like an external function. Let's say here we have used, if you remember, the dice loss and the dice coefficient, which are not built inside the TensorFlow. So these are external functions. In that case, we need to use this custom object scope. After that, we have imported some matrices from sklearn, that is f1 score, jcard, precision, recall. Next, we have train test split. I think we don't need it here. Next, we have dice loss, dice coefficient, then load dataset, build unit. Okay, so things are done. Now let me just copy some more thing, because they are repeating. So it's better to just copy paste them. So here we have the height and width initialized earlier for easy use. Again, a function to create a folder. Now let's go to our main function. I'll copy it from my code. So this is the main function. From there, the execution starts. So now in the testing also, we're going to see the environment. Make sure we have same reproducible, not same randomness. Then we're going to use this function called create dir to create another folder called results, and in this folder we're going to save our predicted mask. Now next task is to load the model. So what we're going to do, we're going to say with custom object scope, and inside this we're going to have a dictionary, the name of the function and the function itself. Okay, dice coefficient. Next, dice loss, name of the function and the function itself. And inside this we're gonna load our model. So we're gonna say model equals to tf dot keras dot models dot load model, just path, that is os dot path dot join. So this is the path for our weight file, which is in files. After that, models.h file. So we have loaded the model. So we're gonna simply say model.summary just to check whether this is working or not. Let's wait. Okay, so you can see the model summary which have names, layer, connection, everything. So this means that we are working fine till now. There's no error. Let's remove this. So now we need to load the data set. So let me just copy that part directly from here. Okay. So for now we need just test images and mask. Okay. So now we come onto the evaluation part. Evaluation prediction. So first of all, you're going to predict and then evaluation. So let me write prediction and evaluation. Because first of all we take the test image, we predict the mask, then we take the predict mask and the ground truth mask and we evaluate. Okay, so let me just have an empty variable, a list called score. Then we're going to loop over our test images and test mask, x comma y. So this indicates the individual image path and mask path. And here we're going to use our tqdm, that is progress bar. Zip, inside we have test x, that is test images, and test y, that is test mask. Then for tqdm we need to write a value, that is how many times this loop is gonna run, that is the length of test x, because both test x and test y are equal, so you can say test y also. So now I'll just print x and y just to show you, and I'm gonna break it. You can see the image path is this 88833.png and same name for the mask. I just want to make sure that they both have same image and mask. And if you see this progress bar, it just stop at 0th iteration. It does not begin from here, so it would begin something like this in order to be completed. Let's move back to our code. Okay, one thing, from this path we need to extract this name and extension also. Let's work on that. So we're going to say name equals to, so we're going to split the x. Okay, so based on some value. So if you see this path, it has this slash. Just copy it. Maybe if you are on Windows, this slash would be different. So just make sure to print the path and then do see. Just try to understand how it works. Don't directly copy paste it. So I just put a slash here. Now I'll just print this name and you just see what happens. Okay, just try to understand the logic, which I mean. If you see now, this path breaks based on that slash. So slash disappears from it. You see, first this slash, then media, then slash. If you see here in the list, blank, then here is the slash, then media, then slash, then nickel. So just split based on that. So our required thing is in the last. So what we simply going to say, minus 1. You can see we have successfully extracted image with extension. Now the name part is done. Now it's time to read the image. Let's write a line here also. Extracting the name. Next task is reading the image. Now I'll just directly copy paste it here because this thing is repeating. We have done the same thing in training. So first of all, we're going to read it as a RGB image. We're going to resize it. We are going to normalize it. And now we're also going to expand its dimension. Because if you remember, the model take the images in the form of batches. And now here we have single image. Okay. So this would be a batch of one image only. So let's show you here. So here it would be something like height by width, number of chain, like this. So let me just copy this. Here also it would have something like this, just height and width would change. Here also. Now here what happened is it would extend the dimension to this. So this now would be a batch of one image. Now we're going to read the mask. Here we need the mask to evaluate its performance, to calculate different matrices. So we just read the mask as grayscale, and what we do, we resize it appropriately. Now we're going to make the prediction. Just the first part in this prediction. What we're going to do, we're going to say y print, that is prediction. Y refers to mask. That's how I use this variable name. Y print means the prediction part. Model dot predict x as the input and verbose as 0. Okay, now what I'll do, I'll print the shape of y. Now if you remember, the input is a batch of one image, so mask would also be a batch of one. Okay, but still we're gonna print the shape and I'll show you how it works. So if you see the shape, it's a mask. Okay, so this is a mask 256 by 256 by 1 and is only 1. So we're gonna say 0 here. So we get our required mask. So next, if you see, it has this dimension. We don't need this dimension. So what we're gonna do? We're gonna squeeze it. On the last axis. So let me just save it and run it for you. Now you can see the mask is of size 256 by 256. This is the predicted mask. Now what we do, because the values of this mask is in the range of 0 and 1, it can be 0.1, 0.2, 0.3, 0.4 till 0.9 or even 1.00. But we have two classes, that is 0 and 1. So we're going to put a threshold of 0.5 here. So value greater than or equal to 0.5. Okay. Or 1 greater than 0.5, less than 0. And now we convert it into integer 32. So this is our prediction. Now what I'm going to do, I'm going to save this prediction and show you. Okay. So what we do, we'll take the original image, the mask and the predicted mask, and we're going to join all the three images into a single image and see. So this would give us a better look. We can easily compare the predicted mask and the ground truth mask. So let's write a line is saving the prediction. So we need a save path. So we're going to say save image path. That would be our folder. If you remember, we have a folder, this results. Then okay, so we're going to not use this way. We're going to use os.path dot join results, the name. So we have the path. Now we're going to write a simple function called save results. First is going to take the input image, this image, then the mask, then the prediction by print, and next is going to take the save image path. So let's take this and build a function. Okay, so now one condition is there, because all the three, image, mask and vibrate, have same height and width, that is 256 by 256. Just that image has three channels and mask and I think vibrate have only one channel. So we need to make sure they all have same number of channels. So what we're going to do, we're going to make sure that both mask and vibrate have three channels, that is same as to image. So first of all, let me just print the shape of all these three arrays. Mask dot shape, then vibrate dot shape. Let me just run it for you. So you can see it has three channels and these are one channel, one channel. Okay. See how the difference would occur. So first of all, we begin with the processing of mask. We're going to expand its the dimension of the mask on the last axis. For this, we have a function called np.expand dims mask axis -1. Same we need to do for the vibrate. Let me just copy it, vibrate. Now just see, let me just save it and see the how it changes. You can see now we have this channel here, one. Now we need to make sure they have three channel instead of one. For that we're going to concatenate these mask and prediction three times. So mask equals to np.concatenate. These should be small. We're going to say mask on the last axis. This is done. Now we need to do the same for the vibrate. We just change the name here, save them and run the program. Now you can see all the three arrays have same number of channel. Okay, so just make sure they have same number of same height, width and number of channels. So that will make them really easily to concatenate with each other. Okay, now for, if you remember, the prediction has the value in the range of 0 and 1. So we need to make it in the range of 0 and 255 so that we can see it. So we're going to multiply it by 255. So when we multiply 0 with 255, it became 0, that it would remain black. And when 1 multiplied by 255, it would become white. So we can easily see it. So we differentiate them as black and white. And that is how the ground truth mask looks. Now what we do, we're going to say cat images. And we're going to need this function. And here we need to say images, image, mask and vibrate on the axis 1. And we're going to save them. Save image path. And the array would be cat images. So let me just run this an example and we can see. Okay, so here you can see we have some issue here. Okay, Let me just check. Save result this, and where the error is, it's here in the cat images. So let's just have a look at it again. First we need to give the path, then we need to give the array. Oh, my mistake, it should be 1, not -1. -1 means the last axis and it would not concatenate on that. Okay, it would concatenate but it would not save as image. Yeah, right. Because let's say we concatenate it on last axis, so it would become 256 by 256 by 9, because 3 channels here, 3 here and 3 here. So that is why if you save an image with 9 channel, it won't save. So this is the reason it's not working here, because it say either channel should be 1, 3 or 4. 9 is not like. 1 is for grayscale, 3 is for RGB and 4 is for RGBA, because there's alpha layer also, like in PNG images we have an alpha layer. So now I'll show you that one image. So this is that one image where we have first the input image, ground truth and the prediction. But one missing thing here is that we cannot separate them. So for that we'll make some changes in the code. So what we do, we're gonna have a thing called line. We're gonna make a small white line. np.once height, width should be 10, channel should be same as the rest. So what we're gonna say, a simple line here, a simple line. So now we're gonna run it again. Now we can easily differentiate. Okay. Now if you see input image, ground truth and prediction, now you can easily see 3 images. Okay, you can make this instead of 10 by 5, it's up to you. But now in this way we can easily compare. We can easily compare both the ground truth and the predicted mask. Okay, now this saving the image part is done. Now we'll work on the evaluation part, because we also need to evaluate the prediction against the ground truth and calculate some matrices. Now we'll calculate the matrix values. So first of all, let's calculate the f1. F1 is also called dice, because both f1 and dice have same formula, especially for binary segmentation. So we're going to say f1 value, then we're going to call the function f1 score. First we're going to give it, oh, one thing we have left. Okay, just let me write this code. Then labels equal to 0, 1 and average equals to binary. Okay, and before writing all these, we need to make sure we flatten those arrays, both for the mask, okay, and for the prediction. So we have already applied the threshold, so we don't need to write this line. We simply ignore this and write mask dot flatten, just that, it would work. So this is for f1. Like that, we're gonna have 3 more matrices, and these are the card, that is mean IOU, recall and precision. So we're gonna append these values along with the input image name in the score. Score we have name, f1, Jacquard, recall and precision. So now I'll copy paste some code. I'll remove the break from here. So now we're going to write the code after outside the loop. So if you remember, for score, okay, first is the name. So what we do, we have this small score written here, and it contains the matrices after 1. If you see, after 1 everything. So from this, that it extract all those values, then it calculate the mean score, and we print out these 4 matrices here. And we can also make a CSV file of this. Okay, So we're going to save this and I'm going to run this here and we're going to test the score. So now you can see the progress. Okay, there's some error. Okay, so it says target is multi-class but average is binary. So I know what that error mean. So it's getting a continuous value. For binary it should have 0 or 1. Okay, it is, oh yeah, it is for mask. For mask we also need to apply this thresholding because some things are also there here and there. Okay, so for mask we need to do something like mask divide by 255. Okay, now we apply thresholding and it should work fine. Let's run it again and see if any more error is there. Okay, now you can easily see the progress bar. So this way we can easily see how much iterations are done out of 612 and how much time it's gonna take. So it's gonna take 30 more seconds. It has taken 15 seconds. So this is a much better way than to see the blank screen, because if let's say it's for 10 minutes, cannot continuously stare for 10 minutes the blank screen. But with this way you can easily see that let's say 50% is done, 60% is done. So you feel more satisfied with this progress bar, and you also know how much time it's going to take, so you can just put that time into some other task and come back again. So it is done. Here you can see the scores. F1 is 76%, Jacquard is 67%, recall is 75%, precision is 81%. So these scores are okay, but I'm not going to say these are really good. These are just okay for me, not really good. But with UNET I'm not expecting very much good, because that model came in 2015 and it's 22. I think it's 7 years. So there's a lot of improvement in those 7 years. So over the next few videos we're gonna have more architecture and we're gonna try to improve the performance by using different architectures. And now I'll also show you the results which we have saved. Now we can easily see image, mask and the prediction. You can easily compare and see which image lags. Like here you can see this over segmentation. So this, for this case it's over segmenting. So like this you can see different cases. And if you, I'll show you this course.csv file. So now even you can see for individual image what is the score, what is f1, Jacquard, recall, precision. Let's say for some case the score is okay. You see this, for this image the score is really low. It's like 0.2 f1 and that is not really good. So let's search for that image and see. You can see for this case it's a really bad score. So this way you can analyze your score, okay, and this would help you to further improve your performance. So I hope you really enjoyed this video and understand how to use UNET and how to train it and test. So if you are still here till this end, just make sure you like the video and subscribe the channel, and please do write down below if you have any query, comment, anything, or even you can write some comment. It would help to boost the video, because I know there's really long gap of 6 months between this video and the previous video. So just for that I'm really sorry, but for now I'll try to make at least one video per week. So help me to boost my channel, but by liking it, subscribing, share the video and comment below. So for now, thank you, have a nice day.